Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today I would like to welcome Professor Kong from UCLA Computer Science Department to Microsoft Research. He'll be talking about converting C code to FPGAs. I want to present Professor Kong as one of the, I would say, brightest stars of electronic design automation over the past probably 15 years in all of academia as well as industry. He has done pretty much everything that there is in academia. He's a chair of the department. He has you're an IEEE fellow. Produced a couple of students who have ended up at Wisconsin, UT Austin, UIUC, etc. He has had a startup sold to Magma. He's the chief technology advisor to Magma. There's just tons of things. I could just spend pretty much the entire hour introducing Professor Kong. I think the best thing is if we start down to the technical talk. Thank you, Jason.
Darko, thanks very much for the introduction. It's my pleasure to be here. In fact, even before walking into the room, Darko has been lower my expectations, saying you may not even see people because people can sign up remotely. In fact, that was my expectation as well, because I always associate the name Microsoft with sort of software, leading software research. I even didn't expect the topic would generate interest, so I appreciate your being here. But I think it's getting to the point that the boundary between software and hardware is blurred quite a bit. There's also a lot of opportunity to use some of the techniques I'm talking about for accelerated computing as a new computing platform in general. So as we go through that, I'll be happy to take questions and have some discussions. Since this is my first time talking at Microsoft Research, to give you a quick overview about some of the things we're doing. So we are looking at we are actually looking at a number of topics from physical synthesis with scalability, variability, and also the novel on-chip interconnects for communications. In particular, we're looking at the 3D designs and also using the RF interconnect for on-chip communications. This is actually very useful for multi-core type of designs. 3D will cut down the communication between the different cores, core to cache, right, and having a new type of configuration. The RF, I will talk in a moment, is that give you the capability to multiplex multiple channels on the same physical media, so allow you to have a reconfigurable interconnect. And the topic I'm going to talk more today is on the electronic level synthesis from behavior level, system level. Let's see. I'll just come down to this slide to talk a little bit about 3D. It's a DARPA-funded project at UCLA started about 5-6 years ago. We have developed a fairly complete system. By the way, today, if you go to any EDA vendors, CAD tool vendors, you want to buy a tool suite to do 3D design, that does not exist. So this is typically how that works, is that the DARPA or the NSF will put in research dollars to enable a technology first, and then the industry will follow. So in this case, we have actually in the second phase, we have a joint project with IBM, Penn State, and UCLA. So we pretty much created a physical design flow from 3D floor planning, placement, detail routing, and then interface with the commercial routers, either Magma, Cadence. And all of this is on the open source data model called the Open Access. If any of people here are interested to do some architecture explorations, that's actually very useful. We have several papers using this as a kind of a physical prototyping tool, just to say, hey, if we can actually design things in 3D instead of 2D, how much will impact on latency, power, and so on and so forth. This is a quick introduction about the RF part, where we have done a lot of work looking at the novel interconnect schemes. What we have so far is that you can see that today, because of the power, the limitation, we limited our communication bandwidth, the processor performance more or less to 4 or 5 gigahertz. However, the basic transmission line, if you look at it on the today even 90 nanometer process, we can carry somewhere around 100 to 200 gigahertz of signals. And so we are only using 5% or less than 5% of the bandwidth available. So the idea here is that they're working to multiplex multiple communication channels on the physical wire, which is a well-terminated transmission line. And by doing that, I can actually have a totally reconfigurable system. Of course, you also get the benefits is that goes at the speed of light, right? It's a much higher bandwidth. But the more important part is that in a kind of a multi-core, many-core system is that I can talk to you on demand. We can create a channel and at a particular frequency. If we need to talk a lot more, we can grab more frequencies. When we're done, we can release that. Someone else can talk. So this work actually just published in HPCA conference back in February, received the best paper award. Seems to be the community really like the concept, is looking in this direction. So this is kind of the idea. You can still have your let's say mesh network, network on chip kind of arrangement, but you can superimpose a freeway on top of that. And with that, you can actually get for example, different access point. They can actually can create different shortcuts for you to have dedicated communications. So in sort of at a very high level, you can think about you have a surface street, you can build a freeway on that, and then you can have a kind of a reconfigurable interconnects between any 2 points. Or actually, you can have a multiple pair of them talking simultaneously. The number of pairs determined by the number of channels we can multiplex on the high-speed transmission line. Okay. So, but where I want to spend a little bit more time to talk today is on this electronic system level design automation, where we have done is actually take to kind of enable the design abstraction from the current VHDL Verilog into a higher level. So why we're interested in doing that? And the first, if you really design a customized chip, which Decroset has been our research focus at UCLA in my lab. So we worked with almost all the major semiconductor companies very closely. So you're looking at a 10 million gate to 50 million gate. But even at 10 million gate, it takes you 500,000 lines of RTL. So it's a lot of code to create. I'll show you later on is that by moving sort of up the level abstraction, you can reduce that by roughly a factor of 10. And then also almost all the sort of the interesting SoC design, system on chip designs, you have either one or multiple processors there, right? So it'd be much nicer, you can actually use a common specification and basically a C-like language. So part of that goes to the embedded processors. The rest of that can be compiled, synthesized into the hardware. Moreover, there's a lot of a push in the hardware community to just be able to have executable specifications. No one's willing to dive into writing half lines of VHDL Verilog code from a PowerPoint specification. So they want to have a higher level execution model first, and then validate that model, and then refine it into RTL. So if you work into almost all the major semiconductor companies today, they have actually a lot of models written in C or C++ or variation of a C, which is called a system C. Basically, it's a C++ program with a special class of extension libraries to describe some hardware behavior in communication, synchronization, and clocking, so on and so forth. So in a way, that the community or the industry is also ready for something of this kind, because it reminds me the revolution we went through 10, 12 years ago. Remember when Verilog language first introduced, that was not intended as a synthesis language, right? Because the Verilog allows you to write models at the RT level, register transfer level, can simulate 100x, 200x faster at the gate level. So a lot of people start coding things in Verilog or later on HDL just for the purpose of simulation. But once you have all those models available, the question is that why should I refine it manually into gate level specification, netlist? Can we automate that process? That's where Synopsys started the revolution, so we can all design the RT level now. So I think we are at a similar transition point. If we can enable people to design circuits, actually just use C, C++, and then refine that and into the traditional RTL. That's actually where we want to kind of go. And then finally, I'll show you that once we have this technology, that it also create a capability of doing so-called accelerated computing or reconfigurable computing, and where you can couple the CPUs with FPGAs, that kind of a platform to enable a much higher performance with a much more reasonable power budget. Okay, so that's where the reason what we have. So the research started at UCLA in the year 2000 when we started kind of looking into this direction. For me personally, to start working in this area, also for another reason, because clearly in the chip design today, the performance is dominated by the interconnect wires. There's a lot of concern saying that we cannot scale the performance any further, which is true. But then at that time, we also realized not all the long wires are bad. The long wires you have to cross in a single clock cycle is the performance bottleneck. If you have a long wire you can cross in multiple clock cycles, that's fine. I said, okay, this is a great idea. Maybe I should develop a synthesis system so that I allocate multiple clock cycles for every long wires. So we looked at along that direction a little bit further, but it turned out that if you want to do that kind of optimization or synthesis, you cannot start with the existing RTL specification, because by definition, RTL is cycle accurate specification. It tells you what to do every clock cycle. You may actually make a mistake as a designer that you don't give me the freedom to optimize. So I really want to have the total freedom to schedule the computation and also communication simultaneously. In order to do that, I have to move up to the behavior level. So of course, once we started doing that, we also see a lot of benefits just moving higher level for design productivity, for verification, for a number of other things. So this is the prototype system that we have developed at UCLA, and later on I can also mention a little bit about the commercialization effort. So we have a system, we can take C, C++, system C as an input, and on the other side we can take the platform descriptions, for example, whether this map to FPGA, whether map to an ASIC, it's an FPGA, whether it's Xilinx FPGA, Altera FPGA, it's an ASIC, it's a 90 nanometer, 65 nanometer. And then we compiled it into a system level data model where we have the capability now to map it into, is there a pointer I can, it can map it into sort of three different alternatives. One is that you go to customize the hardware and through behavior synthesis. And the other one is to go to customized processors or standard processors. Doesn't have to be one, could be multiple of them. And then finally, you can also generate the interface to put everything together. The part I want to talk a little bit further today is about this automated the hardware synthesis part. So from a C-level behavior specification, we can come down to, first we go through a number of compiler-like optimization transformations. For example, loop unrolling, pipelining, the strength reduction, bit width analysis, optimization, memory analysis. I didn't list all of those. For example, you also have inter-procedure analysis, so on and so forth. So this effort actually on the compiler side, so we decided to take a hybrid effort. A lot of previous effort, people start writing a dedicated compiler for that. I think it's probably wrong, because this is where the community has done a lot of research. It's the best to leverage an open source compiler where you can kind of take all the existing effort and then add the hardware specific passes on top of that. That was actually the approach we took. I do not know how many of you are familiar with the LLVM compiler from University of Illinois. So that was the one we actually used at the base. It seems to me that it's very big at Apple. It's an open source effort. There's 10, 20 engineers from Apple check in, check out code and all the time. It's a very active effort. From what I'm understanding is that that was the kind of the next compiler framework they're going to move to. And then, of course, now our core research here is on sort of scheduling, resource binding, in how do you generate very efficient, competitive hardware. I guess no one will argue with me about the motivation of doing something of this kind. The question is how competitive you can be, right, in terms of quality. So that I put in a lot of effort. I will tell you a little bit about the algorithm we are doing at a very high level. And I also have some one-on-one time. I'll be going into more details. Then finally, we generate the VHDL Verilog. We can also generate System C. So you can simulate it without any license because those are just C++ programs. The target can be FPGAs, can be ASICs. So we also generate the constraints. The constraints could be like a multi-cycle constraints, the force path constraint. We also have a plan to do very aggressive power optimization. By the way, this is a unique advantage when you do kind of a synthesis from behavior level. For power is a big constraint, big concern. So how do you minimize it? Really, the most effective way is just to shut it down when you're not using it, right? So today we are doing coarse-grained power optimization at OS level, at system level. So if I'm not using the disk after 30 seconds, I can shut off the disk. But in fact, even when you are using the disk, if you look at the disk controller, there might be only 15% of circuits are active at any given point. The other 80% are not active. But the designer does not have the capability to go in to shut down the circuit one by one at the very fine grain level. So that's the technology we can provide because we do the entire scheduling. Remember, we schedule the computation to all the resources. We know exactly what is going to be on, what is going to be off. We had that idea for a long time. It used to be the case there's no way to communicate to the downstream implementation tool. I can say, okay, I'm going to shut down this multiplier for 16 clock cycle. I'm going to let it on for another 4 clock cycle, right? How do I tell the implementation tool? There's no way. Only until very recently, a few months ago, the industry get together, the Synopsys, Cadence, Magma, they create a format called the UPF. How many of you have heard about that? The Uniform Power Specification. So allow us to go from a high level, to kind of pass the design intent. So they created a format. It was not for this automated tool. It was really for human designers, right? If you're an RTL designer, if you're really very careful, very clever, you can say, okay, these things go to high VDD, this go to low VDD, this one will be off, So we think that's actually ideal for us to pass the information to the implementation tool. So that's also a very active research area. Just I want to show you one slide about the result first, just to convince you that we can do this. For example, this is the result from 2 years ago from one of the industry partners. They gave us an MPEG-4 profile decoder. So they kind of chop it off the entire design into a number of blocks. So these are the modules within that design, and these are the sub-modules. And these are the number of lines of C code you can have. For example, you can have a copy controller, motion compensation, there's a parser, variable links decoder, so on and so forth. Altogether, it's about 5,000 lines of C code. And we can take that to synthesize into VHDLs and in the automated fashion. So altogether, we get about 56 or 57,000 lines of code. So in terms of code density, we get a reduction about 10 to 1 or 11 to 1. Not only that, so this one works that we map it to a Xilinx FPGA. These are the number of slices you have. Altogether, it's about less than half of the smallest device Xilinx has at that time for Vertex 2. And also it works at 30 frames per second as required. So the design can also be very competitive. So that's one example. Later on, I'm also going to show you some design that compared to the sort of manual designs. So these are the logic we use. These are the embedded memory we use.
How are you shutting off compute units?
I'm sorry?
How are you shutting off components?
So this one, we're not doing that. The FPGA, you cannot do that. But with the customized ASIC design, right, so we can do that. Where we can, so today power is a big concern. So that when it got down to 45 nanometer, 65 nanometer, they provide you with standard cell libraries, but they also provide you so-called empty CMOS, where you have the capability to have your power rail connect to the real power rail through a sleep transistor. So when you are now using this part of a logic, I can just cut off, I can just turn on this sleep transistor. So this small proportion of the circuit will be off. Okay, I think I can. Well, right? Yeah, so that's the way to solve the leakage, because you can do a lot of things to help with the dynamic power. The leakage is the only way just to turn it off when you are not using it, right? So, but you can see, I mean, I can do it at a very fine grain level. I mean, the 3 multipliers, a chunk of, let's say I'm not doing motion compensation, I can just turn off that mod. So this is very scary for the human designer to do that. They just cannot think at that level of a detail, right? So these are kind of the things perfect for automation. So the advantage you can do that is quite clear. As I said, first, if you write your model at a higher level, it's typically 1000x, 100x speed up in simulation time. I show you can do better code density. And also, more importantly, you can do a very rapid exploration. I will have some example to show. And finally, there are two kinds of exploration you can do. One is that you can explore the boundary between hardware and software. So in that MPEG-4 design I show you, maybe it says not all the modules are equally important. I can implement some of them on the embedded processor, some of them on the customized logic. So that if you start with a uniform, the C-like specification, you can experiment that. The second thing is that even for the same behavior model, you can try different latency frequencies. So if you go with RTL, you just say, okay, we're going to implement the thing at 250 megahertz, so also 500 megahertz. So you set a target. There's a team of people working on it for several months. You get a design. But with this one, we can say, okay, what happens if you go with 500 megahertz? What happens if you go 400 megahertz, right? Each one of them will give you a different area, more important, different latency, and different throughput, and also different power. So actually, I believe we can get a better result than human designers for multiple reasons. One is, I told you, this power. The designers, it's very difficult for them to deal with at that fine-grained level to decide who is on, who is off. And also, you have to make a lot of decisions when you generate RTL code. Some of them, of course, are very experienced designers. They say, okay, I know every trick, every trade-off. But a lot of them, they say that where they're starting, they have a limited experience. For example, just on the FPGA design, you have two computations. You have to decide whether you share an adder or not, or you share a multiplier or not, right? So if you share it, what it means, you have to have a multiplexer in front of that. And then you can decide what time this data goes through. But you have to remember that is the area multiplexer bigger or area of adder bigger? So if you ask that question, even you probably have done a lot of RTL designs, you may not know because it depends on the platform you have, whether you go to Xilinx FPGA, whether you go to TSMC 65 nanometer. So we actually model all this platform information so we can make that decisions that when we generate RTL code, whether you share or not share, you get a different RTL code. So there's all these things that we believe once we automate, we can actually give you a better result. We are getting to there. So let me give you some examples about the type of optimizations we have. So there's one very important step is that when you from a behavior level model to cycle accurate RTL model. So behavior model, there's no concept of cycles. It's just a computation model need to be done, right? While in the RTL model, you have to say what computation need to be carried out every clock cycle. So kind of an analogy will be you may have Bill Gates or Ballmer say, oh, we want to reach $100 billion next year now. So that's a very high level goal. So the COO, so the president is going to refine it by target, quarter by quarter, maybe even month by month, and the week by week, right? So that's what we call the scheduling. Someone probably also going to do the allocation, saying division by division, that which one should achieve what target revenue, and then department by department, so on and so forth. So that we call the resource allocation. So scheduling is an important step. You give me a computation graph, how do I figure out what computation carry out in what clock cycles? There's the reason it's difficult is that first you have a very different application, data intensive, compute intensive, and memory intensive. And also there's a lot of constraint. For example, you have a resource constraint. I only have finite amount of silicons. And not only that, once you go to a FPGA, they have a different type of resource constraint. I have a number of logic LUTs gates, right? I also have a built-in DSPs. I have a built-in memories. All of those will be constraints. Latency constraints, the frequency constraint, relative timing constraint. And then if you want to do better optimization, you also have to be careful. Some operation can be done in one clock cycle. We call that operation chaining. Some of the operations actually have to be spread out in multiple clock cycles. So that's called the multi-cycle operations. And some of them has to be handled with pipelining, right? So that even before the first operation is finished, I pump in another data. Of course, if you are experienced designers, you can possibly do all of those, right? But still, there's a limit. When you get down to 500,000 code, you have to manage how much optimization can you do for every one of them. So these are kind of we see the ideal opportunity to do optimization. However, we look at the literature very carefully. Really, the problem is very hard So there's basically two kinds of approaches. One is that the people shown the problem is NP-hard. So all they can do is that they use either very simple-minded heuristics. The most common ones you probably have noticed is called the least scheduling. It's not only used for hardware synthesis, it's also used for multiprocessor synthesis. You somehow order all the operations or tasks in a linear order, and with some heuristic weighting functions or priority functions, you decide who to execute next, and then you decide what resources it goes to. So it's efficient, but it's greedy. Another way is that they try to capture all the constraints. So it becomes a linear integer programming constraint. It turned out you can do a reasonable approximation, so almost all the constraints will be linear. The challenging part, however, your variables are integer variables, because you cannot say this operation happened at step 2.7. You have to say either clock 3 or clock 4, right? Clock 3 or clock, so it has to be integers. So that's where you have the difficulty. So we actually make a very significant progress a couple of years ago. We come up with a new type of approach. I call that using the so-called system of difference constraint. So here's let me illustrate that at a very high level. Let's say you have an adder and you have a multiplier. Adder is faster, 2 nanoseconds, multiplier 5 nanoseconds. I have a target clock cycle being 10 nanoseconds. This is 100 megahertz, a slow design on the FPGA. And let's say for some reason, just for the illustration purpose, the resource are only 1 multipliers and 1 adders. Only 1 multiplier is available. So first, you have the so-called data dependency constraint. It's not too difficult to write it down. You have x3 minus x1 larger than 0. Basically, say x3 cannot execute before x1, right? That the v3 cannot execute before v1. I can also have v3 x3 minus x2 larger than 0. So for the dependency constraint, you can actually have that. And then you can look at the frequency constraint. You says, okay, if I have a multiplication, and this is addition and subtraction is the same thing. Can I have all 3 of them in the same clock cycle? No, because if you add 5 nanoseconds, 2, you will exceed this one. So now I can say x5 minus x2 has to be larger than 1 because they have to differ by at least 1 clock cycle, right? So that's type of a frequency constraint I have. And you also have a resource constraint because I only have 1 multiplier. In that case, these 2 cannot be in the same clock cycle. So I can say x3 minus x2 larger than 1 because they have to be separated by at least 1 clock cycle. So if you write down all these constraints, you get a matrix, and you have a variable vector. So this is what we call that the scheduling steps, control steps, right, of those operations. And it's basically a linear type of constraint. Where the difficulty comes from is that these has to be integer variables. So in general, if you write it in this way, it's very difficult to solve. But you probably noticed that when I generated constraints, I was very careful. All my constraints has a form xi minus xj, no larger than certain things. So if you do that kind of a modeling, you can show this matrix has a nice property called the total unit modularity. Once you have that, the total unit modularity, you can guarantee that the vectors, you can just solve that using standard linear programming techniques. You can guarantee you get the integer solutions. So that's actually kind of the one approach we take. Once we have this basic framework, then the question will be how do we approximate all the constraints by this linear sort of a system of difference constraints. So it turned out we can do that very efficiently. Now, let me give you another example, kind of optimization we put it in. So after you schedule, you have data operations in circles, right? It feeds into operations in the later clock cycles. And then once you cross the clock boundary, what do you need to do? You got to store the data, right, before it disappears. So you actually would introduce a few registers. So this is a very sort of a well-understood problem called the register binding. You have to figure out, I have all these registers, these are their life intervals, and how many registers I need, who goes to what register. And we do that in computer architecture design as well, except in hardware design, not only how you assign the variables affect the number of registers, you also affect the amount of interconnect, how the wires are connected. Because I have to introduce multiplexers when you have 2 registers feeding into same functional unit. So that is actually the best possible binding you can have. And I have one execution unit. I have 2 registers. One has 3 input. 2 multiplexers. One has 3 input, and the other one 2. But don't be deceived by this picture. Each wire here is not just 1 bit, right? It could be 64-bit data coming in. So that the multiplexer is huge. That actually, we find out that consume 30-40% of the chip area could just all be a lot of the steering logic. But it turned out if I actually have a register file, then my structure is very simple. That I can actually have a execution unit. I have 2 read ports and then 1 write port. So that's kind of the model I have. And is it easy or is it difficult to get register files? Let's say in FPGA designs, in our case, it's actually not too difficult because for those who have dealt with FPGA, they have this concept called the block RAMs, right? It's distributed throughout the chip. Let me show you. And I used to have a figure. I'll probably delete that. So in Xilinx, Altera cases, they all have tens to hundreds of multiplexers. I mean, the embedded memory block. So those embedded memory blocks are ideal to kind of be the ones to implement the register files. Now here you have an interesting question. So can I divide my entire designs into a number of islands? Within each island, I have a local register file, right? I have some data routing logic, and the rest will be the computational unit. So that's the architecture I want to create. Of course, you can fit everything into one register file. That's good, but most likely it will not be very good because you have a limited number of read-write ports. Your concurrency is very poor. So what you want to do is that you partition your computation into a number of islands and where you can actually do this. So that was also another algorithm we developed, be able to kind of explore the computation, the communication locality to make efficient use of these embedded memories on chip. So we can actually come up with a very significant improvement if you do this using either the discrete register file approach called the DRF versus we use this versus a distributed register file approach versus the conventional discrete register approach, right? We can reduce the area by almost 50% because you make use of these embedded memories. And not only that, when you reduce that much logic, then the clock purity is also somewhat improved as well. And there's also a question, how do you generate this sort of register file island, right? There's different approaches. We also experiment with more efficient algorithms versus less efficient algorithms. So we can also see 12-13% difference there. So this is another example type of optimization you can do. So finally, I'll give you yet another example about how do we do the communication between different modules. So your design is not going to just be one module. Your design is going to be have multiple modules that communicate. How do they communicate? The common ways are FIFOs, buses, and shared memories. Shared memory actually it's kind of a different animal, but FIFOs and buses, they share a common property. What's the commonality between them? I call them, they call the sequential communication media, because the order you write it into the bus is exactly the same order you read out of that, right? With the FIFOs as well. So that's actually one property we explore. But it turned out once you have different modules, so typically in today, by the way, when Broadcom does a design or Intel does a design, they will divide it into a number of teams. So each team will be responsible for one block. So each block itself is optimized, but actually the intercommunication in these blocks can be poor. It turned out actually how you generate the data from this module, because it's going to feed into the next data through FIFOs, right? And then you generate the customer logic block for one, you generate data for the customer logic block for another. A lot of cases people use divide and conquer approach. They will design each one of them independently. But it turned out that the ordering you generate data is actually crucial for the guys after you, because different ordering can enable different type of implementation and also the latency, the communication. The idea is that they will have some dependencies with the data. If you can generate those data first and then go to them, and then you can actually follow up with the data later on. So that's type of one type of optimization we can have. So where we did is that you can actually prove there's a way you can take all the control data flow diagram of all the modules together, and then you can have a way to model those communication channels as part of your scheduling resources. Then you actually have a much more global picture. So we can say then by doing this, we call the behavior and the communication co-optimization. And you can actually end up to have a much better result. So in this case, we have a number of DSP-like applications. And by doing, this is a traditional approach, you design every module separately and then hook them up together using FIFOs. Versus in this case that we actually do the behavior synthesis and the communication synthesis simultaneously. You can see in some cases we get a very good reduction, 30%, 40%. And a big part of that is that how do you handle arrays? When you have array data, do you just kind of produce the data row by row or column by column? Or there are some clever schemes you can produce the data in some specialized order. So that's the kind of ordering we explore. When you actually pass that to the downstream implementation, so basically you have a different way to encode your matrix, right? You want to, but you don't want to really kind of have a very sort of unstructured data passed to the next one. So you reorder the matrix, you still want to actually compress it again. So basically we also have a compression technique to show that you have this unstructured data, I can reorder them, I can still kind of make them into a set of small arrays or some specially structured array. So if you don't do any optimization, you can end up with lots of unstructured data. And once you do that optimization, it's a lot more reasonable. So that's another type of optimization we put it into the system. Okay, so I think altogether we have been doing this research for 6-7 years. The result looks very promising. Some of my students graduated 2 years ago, actually 2.5 years ago. So they were exploring what to do. So one of the decisions they made is that they actually licensed the tool from UCLA for commercialization. So there's a startup company not too far away from UCLA called AutoESL. I'm also an advisor to the company. So doing the commercialization of this technology. So that's one thing that I want to kind of, so they have what they have done a much better job is that they have a very robust language coverage now. Complete support of a C, C++, System C, and then they also have a much better support of all the platforms. For us at university, we tend to focus more on the algorithmic part of that, right? So that the core of optimization engines. They also come up with a sort of a simulation verification flow where you have your, let's say, the test programs, test data for the C models. You can reuse that to test your RTL code you can generate. That actually also very significant. The whole tool was on a kind of a, you can generate your C code in any other ways. So the default for them was to provide you with this Eclipse-based framework where you can do the editing, you can sort of organize your designs, and then you can see the output of that. So that was one design they have. So here is, for example, another design. They were taking that part of the motion compensation to the ASIC implementation. Here you shows the power of doing the sort of architecture exploration, right? You can set your frequency to be 1 gigahertz, down to half a gigahertz, down quarter gigahertz. You try different ones. You can see you generate a very different number of cycles. So basically you get a totally different RTL implementation. The cell count differs by more than a factor of 2. The area also differs quite significantly. Of course, the critical path, the frequency, the total latency all differs because the latency is a combination of a frequency and also the overall number of cycles. So that kind of exploration is also, in my opinion, is very important. That actually affects your design quality very significantly. Yes?
Of 1,000 picoseconds, how can you manage with 900 megahertz? Shouldn't be above a gig?
How do you, so if you, this is a picosecond, so this is basically...
Gigahertz or less or more?
Yeah. So basically that's the resulting frequency, right? So 900, so it's I think it's pretty close to gigahertz, not exactly.
You broke the constraint, no? Isn't the constraint broken?
Yeah, it's the constraint is broken. That, but there's so here's a kind of a classical problem, right? You tell the design team to work very hard to do timing closure, by giving them RTL. There's no guarantee that the RTL can be used to meet the constraint, right? So this is the case. Basically shows you this is you probably wanted to go as fast as possible in terms of frequency, and the downstream tool cannot achieve that. That's actually one data point. You can say, okay, now I can back off, and then there's a different implementation. So I think that spectrum is something we look at it as a result. And then, by the way, it's also not the case that the highest frequency design will be the most efficient, because first it can burn a lot of power, right? And also, if you look at a complete product between the frequency and also the latency, the cycle count, it actually what determines the performance. What I want to show is that by having a single behavior model, you can do this type of exploration very easily in a matter of hours. They also have the flow to take from a system C specification. In this case, it's a kind of data security type of applications. Very similar kind of reduction. You start from a couple thousand lines of C code, system C code. In this case, you generate RTL code in the 23,000 lines. And this is at the TSMC 90 nanometer process, was about 70K gate count. I mentioned there's a simulation and verification flow where you can reuse your behavior test vectors, test bench to test your RTL code. One of the things I want to mention a little bit is that having a tool like this is actually enabled very interesting applications. Of course, the primary use when we developed this technology was for hardware design. It turned out once we have this capability, we can also use it for computation very efficiently. Let me just see whether that's just I want to just switch to another presentation very quickly. I want to say a few words about that. Because I want to show you one slide about, because I promised to show something about the quality of the result of the tool. So this is actually one data point, fairly recent. There's a large defense contractor work with them. They want to implement the 3DES on FPGA, and they actually had a manual reference design. It's basically coming from IP vendor as a reference point. So they have a C-level model. They want to see how that actually impact the design. So it turned out that this is their manual sort of implementation. It's an on-pipeline implementation. When they give the behavior model to the tool can also generate a very competitive design. You can see that in terms of frequency and the throughput will be the same. In terms of the lookup table areas, this is a logic, is actually less. And in terms of number of flip-flops, it's slightly higher. So this is basically very comparable. But it tells you the tool can match actually a refined manual RTL design. But it's more interesting is that by the same tool, you can start experimenting. And this is on pipeline. You can say, okay, if I want to pipeline it, I'm going to feed in data every 18 clock cycles. I believe the hope, if you don't do anything, is actually 56 clock cycles. You get the latency there, right? You feed in every 18 clock cycles. Now you can get the design larger in area. You can see that the logic is about the same, but the number of flip-flops increases because these are the pipeline stages, right? Now the throughput from 200 goes to 600. You can say, I want to pump in data every 6 clock cycles. Now you can get something which is a 10x throughput, and of course with more area and with more logic. So that was the kind of the first you can match the manual designs in a very competitive way. But moreover, it also gives you a lot of alternative solutions. I think that's what it enables. Yes?
What's the input? You said that it was basically a GCC program. How modified was it before feeding it into this process? I'm assuming it wasn't just an unmodified software implementation.
Yeah, first, I mean, there's two things, right? One is that in terms of language coverage, this tool is actually very good. I will show you one slide. So one of the application of this tool is at the investment bank, which actually surprised us initially. So there's a group of people at the investment bank. They want to implement customized circuits to do stock option calculation, financial engineering, all of those things. You can imagine that's probably the reason caused all these the financial system meltdowns by trying to be too smart. So they actually took a very kind of a totally different code, right? I mean, written for a very different purpose. They were able to go through the system. We actually get a very strong recommendation endorsement from them. So in terms of language coverage, it's very good. But it doesn't mean that every piece of a program, once you can pass it through, will give you a good result. So you have to also think about the kind of the concurrency and so some of the structures. For example, I will show you also some UCLA experience we have, use it for accelerated computing. How you structure your code is important. Now, so the internal language coverage is very good. It also gives you the option, for example, like this pipelining, you can actually add pragmas in your code. It says this loop I want to pipeline, and here's the initialization interval. If you don't do anything, they will pick one, right? But then you can also give your own input to that. So there's also, so it will be a C code. The good thing is that the C code, you feed it into autopilot, can always be compiled through GCC, right? But it gives you some pragmas that you can also kind of as a directive to the hardware synthesis.
Was this financial institution using your software or the startup's modifications?
It's always through. I mean, when they come to the real applications, typically goes through the startup. This one is also the same thing because it's just in terms of the language coverage, all of this, that they provide a much better support. Yes.
The data structure of DES has been pretty much pessimized for C. Nothing is of the right size. What do you expect to happen if you have something more sensible like AES, which understands about bytes and memory addressing, rather than funny boxes with 6 wires in and 4 wires out?
Mm-hmm. So I did show a slide, right, with AES. We also tried it with another one. So in that particular application, they chose to use System C. So this is the difference, the subtle difference between C and the System C. System C is more intended as a C++ extension for hardware designers, right? It gives you the control to have a kind of arbitrary precision, the bit vector manipulation, some of the synchronization. So that's for the reason is that when you want to have more control, you probably want to use not the vanilla C language. You want to give you more power, right? To do that. Yes.
Application annotations like unending a loop for pipelining and stuff like that. That takes more of the code understanding, right? Like the people who actually wrote the code have to like profile loops because someone who's looking at fresh code cannot actually do the loop annotations themselves. How long does it take you to like profile an application or annotate an application correctly?
You can use a sort of a traditional profiler to do the profiling. That's very easy. And not only that, you can typically it's an iterative process, right? You come up with some model, you go through the tool, you get to the FPGA, you do some simulation, or even just running it at speed. You can say, okay, this module is too slow. Then you can come back to do that. So it's a more of an iterative process. That they will actually give you the information about the sort of the simulation, the latency of every modules. These some of the marketing slides I will skip. Basically, talk about what's the unique strengths of that. I think two parts I will just highlight. One is the language coverage because we take a very different approach. A lot of these EDA companies they start using their customized compilers to do that. I think that's actually a wrong approach. You want to kind of leverage all the research in the compiler community to build things on top of that. The second thing is obviously all the optimizations we are doing, right? With scheduling, with resource binding, with how to optimize communication and the computation. This fine-grained power optimization, I still think is a very important part that will differentiate that from a lot of other tools. So I want to say a little bit that one thing it enables on domain-specific computing. So you have seen these slides for many times. Clearly, power is the barrier. So the industry current approach is that by going through parallelization. So I stop the frequency scaling, so I will kind of have more cores at the lower frequency. And the question is that how do we go from there? Because you can build these very generic systems with multiple cores, and or you can actually have a large system with many of these compute units, either in a cabinet, in a cluster, whatever. So what we are thinking at UCLA is that, that's one way to go that, but we think there's a lot more opportunity to gain power efficiency by customization. So we think that could be the next trend after parallelization. The reason I'm thinking about that way is that I think we actually have sufficient computing power for most of the applications if you boil down to us. I mean, these presentations, whatever the MSN Messenger, email, you really don't need to run at a very high frequency or very high performance. However, if you boil down to every individual customer or every single enterprise, they do have one or two, a handful of high, sort of a computing intensive application need a lot of performance. So the idea, I think, is natural thing to think is whether we have a way to speed up those application for that particular user of a particular enterprise instead of just raising the level of general purpose computing. So these computing hungry tasks can be accelerated, for example, using either dedicated hardware. You look at the Sun, that the latest announcement, they already include some encryption engines, right, in customized hardware for that. You can have a customized processors. We actually did research at UCLA called the ASIP, Application-Specific Instruction Set Processors. And you can use GPUs. GPU is not very power friendly, but it can give you a lot of performance. So we, in particular, are looking at the possibility of just using FPGAs because it's programmable, right? It's give you total customization for implementation. So it has actually a lot of promise. If you look at the literature, there's a conference dedicated to this area called the FCCM field. What does it stand for? I forgot the acronym, but it's basically customized computing, field customized computing machine or something. But there's two significant barriers. I actually directed the effort even 12 years ago to UCLA, but I gave it up very quickly. First, at that time, the FPGA sits on a peripheral bus. We experiment with the Sun workstation. When it goes through S-bus, get to the processor and get the data back, it's like taking years. So any gain you got from the FPGA is useless, right? The second thing is that if you look at all these papers, they have very impressive speed up now on sort of a numerical computation, on bioinformatics and everything. But all of those are written by lower paid graduate students using VHDL or Verilog. Real programmers will not program in VHDL or Verilog. You have to actually get to C and C++ level. So I think both barriers are kind of disappearing in a way. One is that on the communication side, there's a lot of exciting on-chip, or chip-to-chip communications. So for example, this is the hypertransport bus that AMD sort of enabled, allow you to go from processor, co-processors very efficiently. And the Intel also opened up their French side bus, and you can actually allow very high-speed communication. Even the PCI Express is actually quite a decent bandwidth between the processors with a co-processor. So these things are actually, that barrier is become very small. So the other one, for example, this is the unit we have at UCLA, and I will show you some application we developed where you have the FPGA, the CPU, this is Optron, can go have its own DDR memory, and this is a originally intended for as a dual Optron systems, right? So you can replace one of them with FPGA, and they will be communicating by the hypertransport bus at a very high speed. The second thing is that with this kind of a compilation technology I talked about, really you can go to hardware implementation very efficiently. So this is one of the famous algorithm called the Black-Scholes algorithm for stock option pricing. And when we were working with this financial institute, at the beginning they were skeptical. This is, I will not give you any proprietary data. Why don't you just go to this website to download this piece of code? Tell me the result. So it was obviously now written for sort of a synthesis. But it turned out the only thing we need to rewrite is this power functions. So that because right now you even don't need to rewrite it. Now you can just take that. We can support X to the piece power. And you can take that into FPGA. Really, there's no multiplication of that. You can get implementation on the Xilinx FPGA. This thing runs at only 100 megahertz roughly because clock period is 10 nanoseconds. It's basically a customized machine going through 400 some clock cycles, and every 12 clock cycles you can pump in the data. So we get about 30x speed up over the implementation on AMD machine. So not only that, if you look at the power implication, so on FPGA running at 100 megahertz, you consume about 6 watts of power. If you run it on the AMD processor, it's at 68 watts power. So there's a kind of a 10x of a difference there. If you really want to bridge the gap by having 10 Optron workstations or whatever CPUs, so you are talking about a difference about almost hundreds of x of a CPU power. So that's where we see the potential. We call the customized computing. If this client or this enterprise, that's their primary interest, maybe we don't have to build a very powerful general purpose computing for that. We can have actually accelerate a lot of applications as a co-processors. Yes?
Does that FPGA do actual IEEE double precision floating?
Yes. Okay. I can show you, this is what we do now, what we did. In fact, again, this is the effort done at the Auto ESL, the startup company. So what they did is that they actually added the full support of IEEE 7.5 floating point. So this is even better than GPU because it supports both the single precision and double precision. And also what we added is that the bit accurate, the fixed point arithmetics. So this is not only at the specification at the input that the program will automatically propagate all the bit width information for the intermediate variables. You can do actually generate very efficient hardware. And then the good thing is that for them, the investment bank is music because they really don't want to learn anything about the VHD or Verilog. They have no interest in knowing anything about the FPGA. So they actually support C, C++. So he gives a very glowing quote, and he says, okay, it does whatever. By the way, there's a number of companies that claim they can do C to RTL, but you should ask a little bit detailed questions. A lot of them have a lot of restrictions. For example, half of the company, more than half, will say we do not support structures. So that's actually a showstopper right away, right? A lot of them, then you go, there are a lot of limitations. We cannot support array of structures, structure of arrays. By the way, there's some fundamental limitation you cannot do. For example, you cannot support malloc, dynamic memory allocation, because you cannot generate transistors on the fly, right? And then you cannot support unbounded recursions, because everything is a finite resource. So those are considered to be fundamental limitations. You have to rewrite your code somewhat. But all others are really kind of artificial constraints. A lot of the tools impose. We don't have to kind of face that problems. And at UCLA, I do not know too much about the financial applications. When I saw this, I said, this is very interesting. So let's pick an application I'm familiar with, and I'm in the hardware design area. It turned out the one very time-consuming task today is called the lithography simulation. We use 193 laser to produce 45 nanometer transistors, right? It's a miracle because you actually use a very white brush to paint very fine, right? The small font basically can do that, but it's through a lot of numerical techniques. So in order to do that, you have to solve so-called Hopkins equation that this can solve. It can take hours or days to do that. So I started as a student to do an implementation. Originally, this tool, before the tool available, the research started the early part of last year. So he spent about 4 months to do RTL coding. He sort of get the system working. But then the good part is that towards the last summer, the tool was available. He was able to try the tool just from C to RTL. He did that in about a week or two. So this is the core part of the loop you have to deal with. So just through this project, we also gained a lot of experience because there was a question asked early on, so what kind of C you can take? So his initial C code can pass the tool without any problem and get an RTL, but then you do not get a very good performance. It turned out you have several loops, right? Your loop with the different rectangles, the layout rectangles. You also loop through different level of kernels. This is by kernel decomposition from optical theory. And then finally, you loop for different pixels, right? This is a very natural way to write it mathematically, but it's not a very good way to implement on hardware. I bet it's also not a good way to implement on multi-core CPUs because you did not consider the data locality, right? So what you want is that the kernels, you want it to be reused as much as possible because that just affects your precision, right? You use one kernel to do all the computation and come back to do another kernel. So that actually is easy to do. You can change the loop ordering, that you move the kernel to the outermost iteration. And within that, you have to do some analysis. Do I do process for every rectangle? Every rectangle can affect all the pixels. Or do I do for each pixel, I consider all the rectangles, right? So that kind of code rewriting is just still the human creative part. So it's not saying you have the tool, you can just write any C code and try to do the implementation. We don't need designers anymore. We still need good designers that can think kind of analytically or kind of strategically, where you can make use of the tool to get the best result. So he actually did that, and so eventually we get about 15x speed up that on Optron workstation. So this is about 15 watts we consume compared to 86 watts. So you get about 6x times 15. So that's about 100x about power performance efficiency we can gain. And it's also a fairly successful example we have there. So some of these data points really kind of points us to think there's a lot to be gained by this concept of domain-specific computing, right? So you can actually create customized computers, customized machines with a much higher performance but a much lower power profile that for specialized application or specialized application domains. So I think that's kind of the materials I want to cover. I'll be happy to use the rest of the time for some discussions. Very quickly, I just wanted to show you that there's an ongoing effort we at UCLA to do processor-based design optimization. First is that we can create so-called application-specific instruction set processors. And same thing, that with the FPGA, with some kind of a programmable logic, we can generate customized instructions. So this customized instruction can implement a sequence of applications you're going to execute very commonly, right? So those, we can identify those, and then we can create the pattern libraries, and finally we can generate sort of the unique, the new programs you need to have. So this is what we call the pattern generation, and the pattern selection. We select among these what are the set of patterns should be mapped to specialized instruction sets, and then finally we can generate a new program to do that. So not only that, so we're looking at the possibility of synthesizing the entire design using this kind of a methodology into a number, basically application-specific processor network. So the difference here is that you definitely had to customize hardware logic, let's say using XPattern or AutoPattern, but a lot of others can just be specialized processors. The processor with a different bit width, right, with different instructions, that with different registers file cache sizes. So my view is that if you look at the complexity of the design, you can easily put in 1,000 to 2,000 reasonable sized transistors. Remember that the Core Duo is a billion transistor designs, right? I remember when I entered graduate school, 386 came out. That was a big achievement. That's a 1 million transistor design. So you can put 1,000 386 there without any problem. So my view is that the processors are just the future standard cells, the building blocks. The question is, can you synthesize your design into that very efficiently? So we actually had a very nice progress just recently. We can synthesize application into a homogeneous collection of homogeneous set of processors. This is just one illustration. Let's say these are the task graphs you have, and you can have a naive ways that you have one kind of a processor for each one of them. You have a 10 nanosecond stage delay, 5 stages. So this is one implementation. So these two can be actually on one processor because I have 10 nanoseconds, so it's okay to have them to one processor, execute two of them. So in this case, I get a 4 stages pipeline, right? And so finally, we can actually come up with even more clever implementation that I can actually get 3 stages, still satisfy the 10 microsecond stage pipe and delay. So the idea is that if you think about the processors as your building blocks, you have to think about how do you map a computation to a network of processors very efficiently. So that's kind of the ongoing research we are doing at the UCLA. So this paper was published in FPGA FPGA 07. So we're looking at the various kind of extensions in this direction. So this is another example where we start looking at the heterogeneous system. For example, part of that can all be in microBlaze, that's the Xilinx embedded processors, but part of that also can go into customized hardware. You can see sort of a significant performance gain by doing this trade-off. But I think today, in today's design, what is more important is the power gain. Typically, when you go from a processor-based implementation to a customized hardware-based implementation, you can gain power efficiency by somewhere between 100x to 1000x. So that's actually what will make a difference. So I think the conclusion I want to kind of share with everyone is that I think it's the behavior synthesis technology today is mature enough to handle a lot of applications. The improvement coming from several areas by doing platform-based modeling and by looking at the communication, the interconnect, the optimization simultaneously, and a lot of these advanced algorithms we developed also help to improve the quality of the result. I think at the end, we can actually get the RTL code very comparable to the human designers. Hopefully it will be better, as I said, in terms of the power, routability, some of these very vague metrics the RTL designer has a hard time to deal with. We also kind of looking beyond this is to look at the synthesis at the system level, where hopefully we can make use of both processors and customized hardware to get a lot more efficient implementation. So that concludes my talk.
Questions?
So the last thing you mentioned about the modulus processors, and you had that nice graph showing sort of tasks going from one processor to another. So can you comment on the applications that you're basically targeting for this paradigm?
Yeah. So where we're thinking is that I guess you are referring to this example. So this could be a task graph, like if you have a stream type of application, like a video encoding, the MPEG-4. I think Motion JPEG was the application we used. You can typically decompose that design into a number of modules. And it's a stream processing because the data will keep coming in, and then it will be implemented in a pipeline in the fashion. So typically you have a stage delay that determines the throughput, right? So that's given as a constraint. Now the question is that given that throughput, how many processors do I need to have? And what's the minimum number of processors? What's the minimum sort of a stage latency? How many stages? So I'm just showing you, that was an implementation, naive implementation. You need 7 processors, 5 stages. And if you'll be a little bit more clever, you need, so this case is 5 processors, 4 stages. Eventually you can do it in 4 processors, right? 3 stages. So that's kind of the trade-off we're looking at.
Personal power. Designing tools are not exactly great on that respect, like in routing clocks, for example, they make a mess out of it. So your numbers are taking the tools as they are, correct? Mm-hmm. So if you actually optimize for power, you will be getting a lot better than 300, for example, right?
Sure.
Do you have an estimate on that?
So the FPGA, to be honest, is not very kind of efficient for power in general, right? That was not their effort. But actually, we did a lot of work at UCLA just on the FPGA architecture design. We published a sequence of work shows. In fact, you can introduce the concept of multi-VDD FPGAs, right? You can also have a kind of original clock gating, power gating, all of those. So I believe they are following that very carefully. We actually have a very good relationship with both companies. They have funded UCLA research for about 16 years now, from early 1990s when they were very small. So they're taking a lot of it. But in the current commercial implementation, none of them actually has that capability yet. So really the best way you can do is by optimizing some transition activity, right? And also by improve some data and the memory locality in doing that. So I absolutely agree with you. There's a room to be improved. Clock gating you can implement on FPGA fairly easily because they do have flip-flops with enable signals. Mm-hmm. So yeah, kind of things The same concept when I say fine-grained optimization. If you cannot shut off the power, at least you can shut off the clock, right? So that will help the dynamic power. And that's actually fairly easy to do. I believe the tool does that already. They can actually just generate the clock gating signals.
Have you tried to see like one of those results?
Yeah, I don't have the slides, but they have a slide. I think it was quite dramatic. That was 20-30% of a reduction on power.
I'll have a couple of questions here. So when it gets down to debugging these designs, so when you go from C to the FPGA, if you want to debug on the FPGA, let's say in real time, what are the tools that you guys provide?
When you go to FPGA to debug, we do not provide the specific tools, but the Xilinx has a very nice tool called the ChipScope. I don't know how many of you have used that. They can actually capture basically all the runtime information, and you can read it out. That you can actually look at the signal value.
To get symbolic debugging, I assume that you have some tools to provide back the symbols, right?
Yeah. So
you get some symbol swaps.
The correlation. Yeah. So in general, it's not an easy problem because remember I keep saying that we want to leverage all these advanced compilers, which is very good for the quality of result, but it also messed up the correspondence because they do a lot of. So what we are thinking is that we can give you an option. You can compile using, let's say, -G kind of option. So I do less optimization, allows you to see a better correspondence, and then once you get it correct, you can go back to do more aggressive optimization.
One more question. This is more of a vision question. So there's a lot of speculation on multi-core. People are thinking, there'll be 100,000 CPUs on a single chip, etc. There was a paper from IBM from a couple of years ago where they looked at the thermal effect that you're going to have on the surface of the chip. If the conclusion from what I recall was that if all CPUs are under distress, the thermal power and just in general the power consumption is such that you stop getting any gains from the multi-core architecture beyond, I think the result was around 8 cores at 45 nanometers. So where do you see, mainly because of the leakage, right? So what do you see here? What is your vision there? Do you think that it's going to be so easy to get rid of the leakage? I know that that's one of the major problems right now.
Yeah, I think it's not easy to do that. In fact, where was it? I was just thinking that that's where you need the customization will be very useful, right? And also you can see the type of customization we think about is that each processor can be customized in terms of bit width, register file, cache sizes, clock frequency, supply voltage. Maybe you can have all these cores. They don't have to be at the same clock rate. They don't have to add the same clock frequency, right? So under the instruction set and the degree of reliability. So there's a lot of parameters. And what you also want to do is maybe very fine grain of power kind of control. That even though you are doing the computation, maybe not every cycles that they will be active. So you can do a lot more. So that probably can extend your. Always there will be some limitations in the power thermal constraint. So
do you see like 1,000 core chips anytime soon?
As I said, in terms of the complexity, there's no difficulty to put in 1,000 core chips, right? Where the bottleneck, in fact, one is the communication, I see, and the other one is the power, the thermal behavior. So, in fact, some of the work I mentioned early on about RF was also to address the communication bottleneck.
So the RF architecture, does it consume proportional? Does it have proportional?
No, actually, one thing I should say, RF is actually very power efficient because we're transmitting waves instead of charging, discharging the RC.
Cool. Any other questions? Yes.
So related a little bit to the question regarding the patents, what's happening at real time? Let's say somebody builds a system like this, deploys it in production. How do they figure out that the FPGA is defect free? Do they need to have some? How do they monitor that the particular board is still doing what it's supposed to do? They monitor. Are there any perspective on this?
I see.
So how do you know that the FPGA is default free? So you can do, they have actually test patterns you can use. Maybe at the power up time, you can just, the same thing as you test memories. You can test all the logic, interconnect quickly. And then you can start uploading your application into that.
So this
right.
is part of the, basically when you get the FPGA chip itself, it comes with some of the...
I think so, you can get that. As a research topic, we even look at the possibility of you can have some small logic, just keep testing your entire, at the runtime. So, but that, I do not know whether they provide that or not. But that's some ideas we have. Yeah.
I would just point out the first 5 CDC 6600s did exactly that. They did not have an idle loop. They had a test yourself loop.
Okay.
They were pretty unreliable.
Right. But it's a little bit tricky. So basically what we're thinking is that you have to be able to migrate some logic, right? So that when you want to test this part of a logic, I have to mod it here, and then I can test that. And so we wrote some papers on this type. I mean, I'm not sure how, it's not really in kind of any real system yet. In fact, some of the discussion was a Mildred, that Dark Horse advisor. Yes.
How much progress has been in the 3D IC design project?
I'm sorry?
The 3D IC design project, you have like actual chips coming out in 3D design?
We did a couple of tape outs. One, first we have limited access to the foundry. So the foundry we can use is MIT Lincoln Lab. That's also funded by the DARPA. UCLA, we did one chip, was using that interesting concept called the capacitive coupling. So you actually do not need to have a hole that. Yeah, they don't need UBS. Actually, that was an ICC paper last year. Was a very high frequency at the gigahertz range. I mean, so it was actually a successful tape out. We did a second tape out where we have a microprocessor. Where we have 2 microprocessors, a cache. So that one we got the chip back, but we have some I/O problems of design. So that we haven't been able to kind of boot up the chip yet. But what I'm saying is that you can certainly do that today. By the way, the key part of what we design is the concept of using thermal vias, because it can be very hot, right? We did a calculation. If you don't do anything, that is very difficult to take the heat out. So first you can do optimization, which active layer should be close to the heat sink, which one should be further away. But not only that, you also need to turn out this MIT Lincoln Lab process. It's a SOI process. It's not very thermal friendly. So we have to insert the vias. The vias are the connections between different silicon layers. That's actually very good for thermal conduction. That when you don't have enough of those, we'll put in actually thermal vias ourselves. That's part of the optimization.
Yes, that's the problem. When you start using them for thermal ventilation, right, you get enormous amount of capacitance in those vias. You can't make them that big enough for thermal ventilation.
So we just put in extra vias, doing nothing, but just So that's where part of our optimization will do. There are some interesting studies we can show. You can do that either during placement or after.
Any logic around the vias location, so that
exactly. So we reduce our capacity somewhat,
but it's not that bad. We actually have papers. We have data to show you that it's still reasonable and the amount is manageable.
Any more questions? Okay, so let me thank
All right.
Professor.